Okay, sorry about last Thursday. Hopefully you got the email before you showed up. If not, hopefully you're already here. Um, but actually worked out fine because 8-2 kind of leads into 9-1 anyway, so we'll be able to do them tonight and it won't be an issue at all. So next week, remember there is no class Tuesday or Thursday. It's your week to work on your projects to make sure everything's getting all set up and done. There is an opportunity if people would like, if any of you would like. Professor Allen is doing a STEM, basically, it's like a STEM walk or whatever else on Friday, the 24th from 3 to 5. And they're looking for people to present or to like make like a poster board or a quick little PowerPoint of what you've done for your project. So if you think your project's like good and you really want to like talk about it, let me know or let Professor Allen know, and we can get you on the list there. It's mostly going to be students that are going to be there looking at things and stuff like that. Not a lot, and some of the faculty will probably be here, but nothing crazy. They're just trying to show off some of the cool things that we're doing in the school around the area. So I figured I would give you that opportunity. All right, 8-2. So last Tuesday we talked about the means, and we were looking at basically a mean of means. So, and we were doing the calculations, and then we were trying to figure out what probability things would happen over those curves in that occurrence. Tonight we're going to look at proportions. So remember a proportion. So this is that p hat is just the number of values you want divided by the total number you have. Okay, so p hat is x divided by n. So that is your sample proportion. You can either be given that proportion, and one of the case problems that we're going to do, you're going to be given it, or you might have to calculate it. So, did I not have the other slide there? I did not. Okay, you actually need two other ones. The standard deviation for it is p times 1 minus p over n. And that's the standard deviation of p hat. So those two formulas we've talked about before. The next formula you're going to need, which I'm not sure why I deleted this slide, but it's okay. So before we can actually do this problem, we need to actually figure out if you actually can do it. So this is the calculation you're going to do. As long as that number is greater than 10, which is just n times p times 1 minus p, if that number is greater than 10, it is a normal probability and we can do this process. If it is less than 10, you cannot do that. All right, so write those three down because we're going to need them on the next slide. All right. So, according to the National Center of Health Statistics, 15% of all Americans have trouble hearing. So, this problem then says a random sample of 120 Americans. So, N is 120. P hat is 15%, or 0.15. So 1 minus P is 0.85. So step one, can I do this? So we do, so I have 120 times 0.15 times 0.85. That's got to be greater than 10. I get 15.3. So we can do this. All right, so now that we got that, we know our p hat is 0.15. Let's figure out my standard deviation for it. So remember, standard deviation is going to be p times 1 minus p over 120. So my standard deviation is 0.0326. So that's my standard deviation. Any questions with those two? Yes.
What's the difference between P and
Nothing. It's like standard deviation and sample standard deviation. They're basically the same thing. It's just looking at it in two different ways. So
in the book, they're using P as population.
yeah.
And P hat is the sample portion when the sample was X over.
Yeah, so this one technically would be P because it's the population of 1,500, where the next one, like this one, would be. Apparently, I've dumped it. This one would be P hat because we're actually going to do the calculation of it. But in the calculations, there's not much of an actual difference between that. All right, so if you don't want to actually have to remembering all these different calculators, you can actually just keep using the same one. Even though this says mean and standard deviation, it doesn't really matter. You can still use it. So my mean would be my P, which in this case is 0.15. The standard deviation would be 0.0326. And I want, in this case, at most 12%. So 0.12. Oh, I'm like, wait, why is this not right? Like, why is this not working? That would be why. All right, so we got 0.1787. That makes sense? Great, that's 822. No, actually, I have one more thing I'm going to do with 822. So, if you want, for when you're doing your other ones, I do actually have a calculator for this one specifically. This one. So you can put 0.15 there. My sample size was 120. It does the calculation there and tells you it's normal. And the percent that I'm looking for is 0.12. And it'll do your calculations out for you. And there's your standard deviation right there as well. And they come out to be the exact same number. So, but it's simpler if you just remember to use one calculator instead of having to constantly remember which calculator to use. This one ends up being the most useful one of them all. Any questions on that one? 1787. Yes. Oh, sorry. You're scratching here. All right. Suppose a random sample of 120 Americans who regularly listen to music using headphones resulted in 26 having hearing trouble. So we're going to use the same information that we had before. The P is 0.15. 1 minus P is 0.85. My N is still 120. So that means my standard deviation is still going to be the exact same. But in this case, we don't have the probability. So we don't have the calculation we're going to do. So I need to do 26 divided by 120. And I get 0.217. So let's look at what this gives me in terms of percentages. So all this information stays the same. The only thing that changes here is that's 0.217. So I have in my sample 0.217 or 21.7% of my sample has a hearing problem. That shows up at a z-score of 2.055, or about 2% would be above that point. Or if you look less than, we're in the 98th percentile. So, what would you conclude about this sample? So what conclusion can we make? Is your sample normal? Is your sample expected? No. Why? Yeah. Well, it is above. It's less than the 5%. So yeah, that 5% is my threshold, right? So this is less than that 5% threshold. So this would be an unusual occurrence. So what can we say about people who wear headphones? Would you expect them to have more hearing problems than normal? 15%. Yeah, the first one said 15% of all Americans have hearing problems. That's why P was 15% or 0.15 in this case. So would you expect people who wear headphones to have more hearing problems, or do you expect that the 15% really isn't accurate? Which one of those makes more sense? 15% is what we'd expect. That was the expected value. So if this one's at 21.7%, which has a chance of only happening about 2% of the time, then that's unusual. And in this case, I'd make the claim that people who wear headphones probably have more hearing problems than the normal American. And based on the fact that we all basically wear headphones now, I'm going to guess that 15% is going to be going up rather soon. So, okay. So that's how we can start to use these calculations to understand what's going on. All right, that was the end of 8.2. That was the lesson I missed on Thursday. So, All right. 9-1 is, believe it or not, basically the same thing, except we're going to start looking at what's known as confidence intervals. So we're going to take it one step further than what we had there. All right. So now they make p hat the point estimator. I love how you use all these names for the same thing. So again, it doesn't actually change the calculation. It's still n divided by x divided by n. That's how we find out any kind of probability. All right, so this one we're just going to look for the point estimator. So in a simple random sample of 1,015 Americans, 18 and older, we're asked, do you consider the amount of federal income tax you have to pay is too high? Of the 1,015 adults surveyed, 458 said yes. Obtain an estimate for the proportion of Americans 18 or older that believe the amount of federal income tax they pay is too high. All right. So let's p hat. Yep. 458 divided by 1015. And we get 0.451. And that's my point estimate. Simple enough. I think I have that in this one. Go ahead, you can take a picture if you want. Ready. All right. In every single poll that you've ever seen, on the bottom of the poll, it says plus or minus 3%. That's a confidence interval. They're doing a calculation. They come up with what's known as our point estimate. And then they have a plus or minus percent based on that. Okay, so their point estimate, their calculation that they did is in the middle. And then based on what we'll show you in a minute how to calculate this, we figure out that percent on either direction. Okay, and by doing that, they get a range of values that would be statistically significant. And using that, they can determine how confident they are and that the actual real values would be within that case. So the smaller, this is the one thing that's opposite of the way you would think. The smaller my range, the less confident I am in it. The bigger the range, the more confidence I have. Because what you're trying to say is what is the population that I'm looking at is the real value between those 2 points. Okay? So the smaller the values on either end, the less likely that it's going to be falling in between those points. The more likely it's going to fall in that points. Therefore, I have a higher confidence in it. When I do calculations, it'll make a little more sense. All right, your confidence interval is that range. The level of confidence. Is 1 minus A times 100%. Fine, I'll write it as an A because they use the A instead of my nice little fishy. A. So the A is going to come into play in a lot of places. So the A is going to tell you what percent you have left over. So, for example, if A is 0.5 or 0.05, my confidence interval is 95%. Okay? If my A is 10, my confidence interval would be 90%. The reason I'm even showing you these is because the other pieces are going to come into play in chapter 10, and the A is what's going to be left over on either when we're looking at that bell curve. That's going to be what's left over on the sides. So when I have the 5% or 0.05, that means I have 2.5% on either side of my bell curve. So when we're looking at the calculations, that's what I'm looking for on either side of it. All right. These are the same things we were just saying before. It's got to be normal, so this has got to be the main piece. N times P, 1 minus P has got to be greater than or equal to 10. They do add one extra piece in this. The sample size can be no more than 5% of the population size. So if we're looking at the whole country, 1,000 people is way below 5%, so there's not an issue there. However, if we were looking at, say, looking at the population of Three Rivers, and I interviewed 1,000 people, that's way over the 5%. So we wouldn't use this. By that point, you basically have what the value should be. So there's no point in going through all the extra calculations. And then your mean is just the P, and your standard deviation is the same formula we just did before. Got them all? All right, so 95%. As long as the data is normally, approximately normal, 95% is going to lie within 1.96 standard deviations. I think I left this slide in there. Did I? I did not. All right. These are numbers that are nice to know. Let's see if I can rewrite. Let me actually do it this way. All right. Hold on. I got to look that one up. I can't remember it off the top of my head. It's 2 point something. Uh, 2.32. Nope, 2.33. So these are your z-scores, if you're ever asked for them. So remember, the z-scores are basically my plus and minus. The z-score tells me how far away I am from the mean. So for a confidence level of 90% or an A of 10, we got 1.64. Technically, it's 1.645. I think the book rounds it to 1.64 though. Your 95% is 1.96, and your 99% is 2.33. Those are your z-scores for these. And it's always going to be plus or minus because confidence interval is in the middle, so I'm looking at either side of those three. Kind of like what they did in this one right here. So you can see how we've got the 2.5% on either side. The level in the middle is what I want. My confidence interval is going to be those two numbers there. So this is the low end, and this is the upper estimate. And my value, my p hat, is somewhere in the middle there. And based on that, I would be 95% sure that the real value is somewhere between those 2 points. Lower estimate and upper estimate. Yeah. Estimate, yeah. Yeah, an estimate's a confidence interval is an estimate. So because we've done a calculation, and then we're going to estimate that they're between these two values. Okay, I don't know for sure. That's why I'm only 95% confident or 90% confident, whatever I'm doing. But I'm pretty sure they're somewhere between that. So that's why they're called estimates. Your point estimate will be your margin of error thing is going to be your point estimate plus or minus the margin of error. That's where that plus or minus 3% comes into play. And that varies based on our data. You'll see where the 3% comes from in a little bit. Just write that part right there. That's the only thing you really need. Okay. All right. All you really need was this piece right there. You don't need everything else. Good? Okay. All right. So here, I'm going to get up because I'm going to point. So this is reality at the top. And this was a estimate that I had done. Okay, I collected data. I got my p-hat there. I did my confidence interval at 95%. So I'm 95% sure when I did this that my value is somewhere going to be there. However, there's always the possibility that I did all that work and it's not in there, like this one. So if you notice, this one is outside of my range. This value right here is below what I really would have gotten. So even though I did this work here, I'm 95% sure that it's correct and that my value is going to fall within this. However, this one's one of those 5% that didn't work. I'm a little lower than what you'd expect to do. So not when the normal person hears, I'm 95% sure, what do you think goes through their minds? It's exactly right. You're accurate. That's it. Whatever you say, I'm going to believe. Because in our mind, 95% is amazing. However, there's still 5% out there that could be wrong. All right? So you have to keep that in mind, that even though you've done everything right, there is a chance that it's not correct. Okay. Don't write all this down. Don't read it all. I'm leaving this in here for a reason because I want to make sure that it's actually part of the information. Okay. A 95% confidence does not mean there's a 95% probability that the interval contains the parameter. It means that I'm 95% sure that the interval could be in there. Okay. There is, even though they sound the same, there is a distinct difference between them. If I already knew the outcome, I wouldn't have to do the work. Okay? You're doing this because we don't know what the actual value is. We do this to determine what we think the actual values are. All right? So it doesn't mean that I know, and I'm 95% sure that there's in there, it could be in there. All right? So slight variation, just not always the exact case. So, and this is the case. Any sample statistic that's in the tails of the sampling distribution results in a confidence interval that does not include the probability parameter. Okay? So there is a possibility that my data, I've done everything right, but it's not accurate compared to what is really going to happen. That is what we saw in 2016. So in 2016, when Trump won and Clinton lost, all the polls up to that point said Clinton was going to win. Their data was wrong for a variety of reasons, but all their math was correct. It just happened to fall in the tails. So they didn't do anything wrong. They were still 95% confident, but it was in that 5% that didn't work. Okay. And we kind of talked about why that was the case when we were talking about in one of the first couple chapters, we're talking about how data can be manipulated and looking at how people lie on things and stuff like that. That's the type of stuff that happened in that case. But that threw the statistics off and pushed you outside of that 95% confidence level. Okay. I knew this slide was there, and I screwed up my calculation. That 99% should be 2.575, not 2.33. Let me actually fix that before I forgot to subtract it, cut it in half. I thought that slide was on here. These three values right here are known as my critical values. So if you get a question that asks you for critical value, that's the number they're looking for. That's that z-score. The 1.645, the 1.96, or the 2.575. I did 98%. I did 1% instead of 0.05%. So don't write this. Write the table if you want to write anything down. Huh? Critical value is this piece. It's telling me what's on either side of it. So like this one, that 1.96, that's my critical value. That's the plus or minus that I'm adding. I'm 1.96 times whatever my standard deviation is. Yeah. Yeah, it's the plus or minus version of it. And the slide's not there. Hold on, I gotta get a slide. This one. All right, so this was the same data that we had before. We figured out it was 45.1%. And the Gallup report, its survey methodology follows. The results are based on telephone interviews with a random sample of 1,015 adults. For the results based on the total sample of national adults, one can say with 95% confidence that the maximum margin of sampling error is 4 percentage points. So, their p-hat is 45.1%. We minus the 4%, so 41.1%. We add the 4%, so 49.1%. That is my confidence interval. Okay. So that means what they're saying is that they're 95% sure that the real value is somewhere between 41.1 and 49.1. So, could I say that based on this data, that half of all Americans feel that the taxes are too high? Yes or no? Why? Very good. Okay. 49.1 is not 50%. Okay. So you have to be careful with that. All right. If it was 46% in the middle and I did the plus or minus 4%, it would have just been slightly over 50%. Okay. Now, even though technically it's at the upper end, it would be like right there. You could make that claim. There is a chance that that's the actual answer. All right. I probably wouldn't. But what you want, so the big piece you want to make sure, the piece you don't want to do is assume that is correct. Even though that's in the middle, that's not the actual value in reality. The actual value in reality is I'm 95% sure somewhere between those two. It literally could be 49%. That's a very good possibility. Okay? I don't know. But it's not right in the middle. That's why when they show you those polls, they will put up on the screen the middle number. And then a little text on the bottom, plus or minus 3%, or plus or minus 4%. So everybody focuses on that middle number and assumes that's the number correct. but it's not always correct. That's why if both those numbers are within that 3%, they call it a statistical tie, because it could be opposite. We don't know, because both those numbers would actually change by the plus or minus 3%. So this is the hand way to do it. You're not going to have to do it out by hand, so I wouldn't write this all down. But this is the hand way to do it. All right, I want to do. We're going to do this slide in a little bit. Give me a second. I'm going to move this one. All right. So let's look at this one. Parent teen cell phone survey conducted by Princeton Survey results had 800 randomly sampled 16 to 17-year-olds living in the United States were asked whether they have ever used their cell phone to text while driving. Of the 800 teenagers surveyed, 272 indicated that they have texted while driving. All right, so what is my p-hat? Good. So 272 divided by 800. 0.34. And we want to obtain a 95% confidence interval for this. Okay. So, wrong calculator. So calculator A29, if you're keeping track of numbers, is my confidence interval calculator for proportions. So in this problem, we've got 272 out of 800. So I've got 272 successes out of 800 as my sample size. There you go. Huh? Oh, the calculator? A29. Okay, so we've got, in my survey, I had 34% probability. So on the calculator, we put in 272 successes, 800 samples. It will verify that that meets the conditions. So in this case, n times p minus 1 minus p is 179.5. So it was well above the 10 that I need. Your confidence level is here. So you can do 90, 99, 90, 95, or 90, or if you want some other crazy number, because you can type in any number you want there. So you can actually type in 88 if you want. I swear. There you go. So it will give you any number you want depending on what Pearson wants you to do. The vast majority of them are going to be those three. So in this case, we wanted a 95% confidence interval. So what this gives you is, oh, that's why the margin of error is. That's why the formula was there. I thought it was a different formula. It gives you your margin of error. So in this case, my margin of error is 0.0328. Hey, look, that's 3%. And there's my confidence interval. So I am 95% confident that it's between those two things. In my margin of error, I'm just going to use E, is 0.0328. Yeah. So that's that plus or minus. So I'm 95% confident that the survey is a pile of horse crap, but that's okay. That between 30% or 30.7% and 37.2% of teenagers between the ages of 16 and 17 have texted while driving. I don't believe that for 1 minute. But that's what their data showed. I think they should have done the survey and actually asked the question, are you driving right now? Okay. So that's literally all you do to find a confidence interval. And even if we did it out by hand, it's basically the same thing. It's just a couple extra calculations. That margin of error formula, which I skipped over because you're not going to accept to do it out, is just the z-score times your standard deviation. So if we look here, it's the 1.96 times, oh, I didn't put the standard deviation on this one, times the standard deviation. Now, if I change my confidence level to 90%, what do you think is going to happen to those two numbers? Are they going to get closer or further apart? If I change it to 90% confidence interval, they're going to get closer. Remember, the less confident I am, the more is on the outside. Okay? So that means those numbers get smaller. So 90% confident, that's between those two numbers. My margin of error is now only 0.0276 on it. If I went up to 99%, they went further. Okay? So that they're a wider range. I know it sounds counterintuitive. That's why I'm showing you this. So the more confident I am, the wider the range is going to be. Right? Because remember, what are we confident in? We are confident in the fact that between these two numbers is the actual real value. Okay? So if I'm going to be more confident, I'm going to want more of a range. Okay? I'm going to want a more spread out numbers to make sure that I'm a little more confident that is actually in there. So my margin of error in this case is over 4%. Can I be 100% confident? Nope. You can never be 100% confident. Just because I'm saying that, I'm dying to see what it actually would do if I put it. Good. It doesn't work. It will let you go out to as many decimal places as you would like, though. You can thank Carolyn for that. Allows you to do any number you want now. All right. Did that. That. All right. how many people do I need to survey to get the error that I want? So here's this formula, and I'm going to write up the whole formula, and we're going to talk about it because there's actually a really important piece here. You're never going to have to do this formula, don't worry. But I want to talk about it. How did we calculate P? What was the formula to calculate P? Right. So I need N to find N. Okay? It's one of those weird formulas that mathematically actually probably doesn't work, but we use it because in the calculations, we're naturally going to know P ahead of time. So here's my formula for this. What is the big thing if we're not going to know N? N is the sample size, right? Okay. Is anywhere in this formula the population size? Has anything that we've talked about today had anything to do with the size of the population I'm talking about? No. That's an important thought. That's an important thing to think and remember, is that I don't care if you're talking about Three Rivers, the state of Connecticut, the population of the United States, or the world population. None of that impacts these calculations. Okay? None of it. So, if we did this formula to figure, this is going to tell me how many people I need to sample to get a percent, or to get my margin of error that I want. So, I want to know, this is my little wonderful little calculation, how many people would I need to sample to get within 2 percentage points with a 90% confidence interval? So my formula, I'm showing you out the formula not because I'm going to have you do it, because I want you to understand what's going on when you use the calculator that's going to give you the answer instantaneously. Okay? Because it's going to come up with a number that isn't going to make sense to you. So the first one tells me that it's 10%. So my P is going to be 0.10. 1 minus P will be 0.90. The 90% confidence interval means it's 1.645. And we're dividing it by 0.02. So this is my formula. So N equals 0.1 times 0.9 times 1.645 divided by 0.02 squared. My N has only got to be 609 people. Okay? Why? I don't think so.
Is that square?
Yes. Yes. %90 confidence interval, 1.645. Okay, that's fine. There's a first for everything. All right, so they want to know the proportion of U.S. population that commutes to work via carpooling. they're talking about the entire U.S. population. Let's assume they're just talking about the entire U.S. population that's working. So we're talking about 200 million people. They have to ask 609 of them. So the next time you decide to go on Facebook or TikTok or anything else like that, and they show you this wonderful, somebody posts a meme with this poll, and everybody goes, well, they didn't ask me. You're right. They only had to ask 609 people. So they don't have to ask a lot of people. All right? That's why I wanted to do out the formula, because I was going to get a number that doesn't make sense rationally. You're thinking, okay, I got 200 million people. I got to ask a good amount of people to get an answer. Nope, 609. Now, most times, I don't know the actual answer ahead of time. So when that's the case, we use 0.5. We use 50%. So instead of using this formula right here, we're going to do the exact same thing, except we're going to use 0.5. And for that, I have to ask more people. I have to ask 1,691 people to get a 2% margin of error at 90% confidence interval. So let's change this to 95%. And let's change that to 3%. What did we say almost every single poll that you've ever seen on ever done says? Plus or minus 3%, right? And they're 95% sure that's what's correct. They only ask about 1,100 people for those polls. They make random phone calls, ask about 1,100 people, and then they put it on TV and say, this is what the entire United States public thinks. Crazy, isn't it? Now, my calculator, if you click find sample size, does this for you. And if you notice down the bottom here, it does show you the formula. So in case Pearson at my lab asks you to write, like put in numbers, all the numbers are there for you too. It assumes it's 5% unless you put a number here. So for example, in the last one we did, they gave you the 0.1%. So you can put that number there and the calculation is done. If you know it already, put that number in there if they give it to you. If not, leave it blank, it'll use 50%. Technically, anything you use lowers that number. So any number you put in there, if it's not 50%, it's going to lower. 50% is going to give you the biggest number possible, which is why we use that, because that's going to give us the best chance of hitting what the actual reality is. But yep, 1,068 people will give you a plus or minus 3%. Let's say I wanted a 99%. I wanted to be extra sure. I don't even have to ask 2,000 people. This is why there's people out there that are pushing for the U.S. Census to go to a statistical analysis instead of counting every single person. It costs a lot of money to interview or ask questions to 300 million people. It doesn't cost a lot of money to ask 2,000 people. And be 99% sure you're right. Okay. So, I'm dying. There you go. Even if I wanted to be insanely accurate, I only need to ask 6,647 people. And I'm at like a 99.999999%. It really doesn't be that big of a number. I didn't believe you would actually believe my calculator was correct if I just put the number in there and did it without actually showing you the actual calculation ahead of time. Yeah.
When it goes back to the 0.5 times 0.5, where was that on? You had the math. You had it written down.
That was right here. It's the those two numbers are 0.5.
Those numbers are 4, 5.
Yeah. So if we do the 95, it's right there. It's the P in NP, or 1 minus P.
So we got 1.96 over.
Oh, that's the critical value. The 1.96 is a critical value. That's this number. It's back here, I swear. There it is. That's that number.
Gosh, okay.
That's that Z-score number. Again, you don't need to necessarily know it for the calculator. You can do you don't need it for the calculator. It does that part for you. Because you just put in the confidence level and it will calculate that number for you.
Okay.
So, and again, same ones, 90, 95, 99, and then you can put whatever number you want in there. So, all right. So yes, that is why the vast majority of people never get asked a question, yet you're in all those samples. But if I was going to ask the people at Three Rivers the same thing, I would still need to ask that many people. All right. So, and actually, if I asked 1,000 people from Three Rivers, I'm well over the 5% threshold. So I don't have a confidence interval at that point. I probably have reality at that point. Okay. Any questions? All right. When you're looking at your projects, this is the type of stuff that you can do towards the end. Do a confidence interval, see how close you think you are to the reality of it, depending on the type of data that you have. We're going to do mean on Thursday. So you can actually see if you got actual mean data instead of proportion data. So see you Thursday. I know what I'm teaching in the fall. Elementary algebra, actually. I got the 0900 class. So
Have you done that one before?
a long time ago.
Hey, how do you get Z charts for Pearson?
Z chart?
You
You
just
don't-
look up Z chart on
Yeah, just search a Z table online if you really need a Z table. Yes.
I have a question. So about the project
Mhm.
for the hypothesis, right? Because I need like 30 individuals.
Yeah, you need 30 pieces of data at least.
I don't need to put 18 between 18 and 46, right? I can just put like 18-year-olds or a random
So
number.
when your random sample is going to dictate what your population is. So if you're only asking 18 to 25-year-olds, your population should only be 18 to 25-year-olds. Okay? If you're asking a bunch of people on random things, then yes, your population can be larger than that because that's just your random things.
Okay. And for the hypothesis, is basically
What do you think is going to happen?
is it gonna like compare with the population to try to do
Yeah.
like a research on the
Yeah.
population? Oh,
Mhm.
alright.
Like, what do you think is going to happen?
Oh,
And then you're going to compare your data to what really happened.
oh, thank you.
Yeah, and then use like, for example, calculate your confidence. Ian's asking about the project.
Oh, so you're going to take, so once you have the whole population data, we know what the population thing is. You're going to look at, okay, at your sample, yeah, right. So you got a sample, right. So you got a sample. So you're going to take your sample and you're going to go, okay, I got this data, and you're going to do, you can do your confidence interval from that data to say, I'm 95% sure that the real population is somewhere in this area. So, but you're going to have a mean. You're not going to have a percent like this. So you're going to have what I'm going to talk about Thursday. Same calculations. Everything's going to be exactly the same, except instead of P, we're going to use mean. Or you're going to use X bar.
Slowly, please.
Okay. So when you do your mean for your sample, okay, you're going to take that number, and that's going to be, I'll actually show you. Because I have it already here, so I might as well just show you. That's going to be your mean. Okay? And then you're going to put your standard deviation in there. And you're going to put your sample size. And you're going to say how confident you want to be. You're going to pick. No, you're going to pick this. Most situations, because your data is medical, most medical situations use a 99% confidence level. So we'll change this to 99. And that's your confidence interval right there. Okay? You too. You're coming tomorrow to go over your stuff, right? You said it-
tomorrow or Thursday.
Okay. Remember, we're not here Friday, so don't wait till Friday.
You're not here on Friday?
Did you see the email yet?
None of us are.
Oh yeah. No, I don't come in on Fridays anyway.
Yeah.
Okay.
So, project? Both. Yeah. You too. Your final piece of your project, you have to make a hypothesis. You're going to say, you can say that, and you're doing one that you literally could look up online because the data is there. You're going to say that people with a BMI over whatever it is has a higher A1C. Yeah, yeah, high, you can put a higher than it with a number in there. That's fine. That's going to be your hypothesis. And then you're going to take your sample data and you're basically going to do a confidence interval like this. And if the number that that confidence interval, your hypothesis is in the middle of it, that would be a good thing. Then you cannot, then if it's outside of it, correct. Correct. That's the hypothesis. Is a prediction of what you think is going to happen. This is what I'm saying. For your data, because it's a realistic data, you can easily go online and see the correlation between BMI and A1C. And you can say, okay, this is where I'm going to look at. So anybody with a BMI of 30 or above has an A1C greater than 4 or whatever, or 5, whatever happens to be. I think it's like 7 or something like that. It's like diabetic, but I can't remember the exact numbers. So you can look that up online. So you have the actual population data because people have done this. So you can make your prediction from that. And then you're going to look at your sample data and see if that is true. If the reality, yeah.
Exact number or no?
Yes, you're going to pick an exact number.
Exact number.
Mhm.
Maybe BMI 30.
Yeah.
BMI 30. The people with BMI 30 and greater.
Yeah.
Have higher
A1C.
A1C.
Yeah.
A1C. Maybe 6.
You don't even have to necessarily pick a number for it. You don't have to pick a number. You can just say, "What's up?" Oh yeah, you're more than welcome. Yeah, I know you're next. Yeah, more than welcome to come and sit up. I'll be leaving in a second. So.
I didn't want to intrude.
Oh no, you're fine. So I wouldn't necessarily pick a number from A1C. I would say you're going to pick your number for BMI, and just say that a person with a BMI of 30 or higher has a higher A1C than normal. If your BMI is 30 or higher,
30 or higher,
yeah, your A1C is above normal. Will be greater than normal. Yeah, whatever.
Maybe.
Yeah.
I can criticize.
Right. So that's going to be your prediction. So then you're going to look at your data, and you're going to look at the people who have a BMI of greater than 30 and say, okay, is their A1C higher than normal? And you're going to do a confidence interval. If that confidence interval, if the normal value is inside that confidence interval, your hypothesis, you're going to say, you would reject it because it's not going to work.
I have to take 99% confidence interval.
Yeah.
Mhm.
And you don't necessarily have to do 99%. You could do 95%. I'm just saying most medical studies use a higher percent. They want it to be more accurate. So, but you're not doing anything like it's life and death at this point. So,
No, it's not more, not all obese
Correct.
people have.
right.
It's higher.
But that's what you're trying to figure out. Is it So not every individual. Oh, you can come in. You're fine.
It's not exact.
Right. So as crazy as it sounds, my BMI is off the chart. My BMI is high. I know I'm overweight. My A1C is fine.
No, it's real. It's real.
Yeah.
But
So
you-
but that's the difference between looking at an individual and looking at a sample. So while there is a chance that an individual could be like that, which we looked at last week, if we look at a sample, the chances of a sample of 100 people doing the same thing is very slim. And that's what you're looking at. You're going to take a sample of 100 people and say, okay, in the sample of 100 people that I looked at, is their data unusual? And that's where your hypothesis comes in. That's where that range that you're looking at, that's where that confidence interval, is it going to fall in?